Good morning, everyone. Thank you for attending our webinar series, and specifically today, this is a quick look at our agenda, so I'll review that with you quickly here. So I'll give an overview of RAND and IMAGINiT, also overview the webinar series, and specifically today's topic. Mark will talk about the different methods of factory simulation, and then Alan will talk about collaboration and coordination with stakeholders, and then we'll wrap up by previewing the next session, as well as opening up for a Q&A at the end. Next, please. All right, so especially for those of you that are new to our company, I'll just give you a quick overview of the structure here. RAND Worldwide is we're a family of technology companies. We create, we acquire, we resell technology and implement it for our clients to improve both their employee and customer experiences. We're got an extensive reach in North America and work globally with over 30 offices and over 400 employees. So last time I talked about our specialized teams, and we've got specialized sales teams as well as over 170 subject matter experts to help implement technology. So over to the right, you'll kind of see our footprint there. If you look at RAND in the middle, that's the corporation itself, and then each of the 4 circles on the outside are our divisions. So I'll start with RAND Sim. What they do is solve the world's most challenging problems digitally, typically using the ANSYS technology to simulate things, but they'll use whatever tool necessary to get the job done. RAND 3D helps customers with the major PLM systems, a lot of times big automotive and aerospace, adopt and leverage the technology that they buy, specifically PLM systems. Ascent is a documentation services group. Really great advantage for us to be able to help companies that start looking at digital workflows, adopt those workflows, and get the money that they spend on the technology back out by ensuring that the users, again, adopt and adapt to the change in the corporate standard. And then IMAGINiT is a large Autodesk partner. That's who we're representing today. And being large is good, but we actually have, again, a significant staff to help implement some of the technologies that we're going to talk about today. Next, please. So Scott and I have been giving you little bits. Scott Bullshire's has been some of the other parts of the series, but we've been giving you little bits about the company as we go through this series. So last webinar, I talked about our specialized teams. This time, I just wanted to summarize really 4 basic pillars of what we do as a technology consulting business. So starting from the left, we've got a specialized team of highly experienced folks that have been in industry and helped industries that will help our customers build their system of the future. So most people don't know that we do business architecture consulting, especially for a less investment than what you would do with one of the major consulting firms. So we're really efficient at that. Our broader industry teams help choose the right technology for any job. So we help you pick the right tools. We also leverage our hundreds of years of experience from our team to efficiently consult and implement technology efficiently. And then finally, as I mentioned about Ascent, we help adopt those solutions through training options and documentation services. So that's really, I think, one of our big differentiators. Next slide, please. And yeah, so about the webinar, I'll just talk about the webinar series here for a few minutes. And in this particular webinar, I'll hit some key points that you're going to hear from the team, and then I'll let Mark and Alan get on to their more specific topics. So In review, our last call, we focused on the use of design data to lay out both greenfield and brownfield facilities. Prior to that, in the first webinar, we talked about moving towards a digital twin more quickly, leveraging scanning or reality capture. And then in this webinar, the team's going to talk about methods to simulate, coordinate, digitally to validate different designs and include people in the process. Next slide, please. So here are some high-level use cases that we support. In particular, in this webinar, we'll focus on some of the cases that I highlighted here. So efficiency and optimization digitally, different ways to simulate and analyze a particular design, collaboration and coordination with internal and extended or external teams, and then ways to reduce risk, and that would be risk of things like making a mistake, as well as considerations for employee safety. So if I'm to boil all this down to why you should consider adopting simulation, collaboration, and coordination workflows, it really supports the value drivers that you see up on the screen here. So what we would be looking at doing is ensuring that your project is going to support your company's goals. The other thing it would do is drive efficiency and accuracy by evaluating a capital project early on and throughout the development process. So a lot of companies that we work with don't necessarily communicate well. They work in functional silos, and they do a good job in those silos, but we think information is critical to be shared throughout the enterprise. We help some of the greatest brands on the planet, small and large businesses, get everybody on the same page when executing things like a capital project or other types of projects. So also make sure that the operation will be able to deliver or over-deliver on manufacturing capacity and throughput or yield. And then finally support environmental safety, health considerations and goals by visibility to the changes, and then also reducing waste. So if I dig into this further, you can see some of the outcomes that these digital workflows support. So things like improving collaboration with the project team. So, think about what if you could have a stage gate process managed by technology that gives visibility to all the key players in real time, or what if you have a system that delivers consistency and traceability throughout the process. So, what if you can better sell a project to key stakeholders using accurate data and 3D experiences, and validate and reduce operational costs before a project is realized. So what did it mean to check for things like safety issues virtually, or even train factory workers virtually before doing it in the physical world? So, and then finally having the ability to do things like optimize for energy consumption, which in turn improves environmental impacts, which so many of our customers talk about, environmental and sustainability goals. Next slide, please. So to wrap this up, in terms of the convergence of design and manufacturing, I highlighted some areas in green that Mark and Alan will hit on today. So these are steps in the process that I think that are often overlooked, and what they're going to show today has a huge return for companies. So things like a discrete event simulation is one of the easiest paths, in my view, to a digital twin. It can be a process that is low cost, but can produce a massive return and risk reduction. 4D simulation can help companies make better decisions, avoiding expensive mistakes, And then simple things like 3D walkthroughs, and eventually AR can save companies a lot of time and money. You know, we have customers that we work with. I work with a major automotive supplier that uses virtual tools to train workers around the globe, which reduces travel costs, staffing requirements. It's a really big deal. So with that said, appreciate you listening to me today. I'm going to go ahead and turn it over to the experts and Mark and Alan to dig further into the details, and then I'll be back with you at the end for wrap up and Q&A. Over to you, Mark.
Thank you, Jason. So let's go ahead and get into design validation. So in our last session, we talked a lot about will it fit, right? That was about layout design of having our digital assets, which we have taken from 2D to 3D or captured through point cloud information, and deciphered, will this fit in our area? What we're going to look at today in my portion will be, well, will it perform? And what will it cost us as a company? So we're going to be looking at different analytic methods as well as different tools which can be available from a simulation sort of standpoint to basically take what we have in a 2D or 3D type world and start simulating and validating those things. When we talk about different types of validation analytics, right, there's a very common usage of traditional tools, you know, things like spreadsheet-driven tools or spreadsheet-powered tools. But there's also an idea of reality simulation, which we're going to take a little bit closer look at with my portion. So when you think about statistical methods, you know, the use of averages for cycle times, resource availability, like if someone calls off a shift, arrival patterns for equipment or product for performance, a lot of these things you try to put into traditional methods, which are still valid for a lot of tasks, start to fall apart when you start looking at predictive or advanced analytics, right? So we really want to try to look at reality simulation in that sense. So it's hard to account in a spreadsheet for randomness and probability distributions unless you're extremely skilled with those tool sets. Or interdependencies between one process or another, different time variables and distributions of that time. How downtime events occur, like when did that downtime event actually occur and how do we plan for planned outages or scheduled maintenance and things of that nature. So there's a lot of things to be said about reality simulation versus putting things through traditional means. And we start comparing the results of these, you start understanding that spreadsheets get knocked out pretty quickly and the reality simulations become the champions for decision-making capabilities. So kind of break this down into some standard vocabulary around validation analytics. You know, there's a chart we can kind of look at here, which increases value of the analytic versus the technological capability of the analytic. So essentially, we live pretty easily in this state, right? A descriptive sort of analytic or hindsight, right? So what happened? We document exactly what happened. This is very common to take data points and then to plot them and to analyze them. Now, where we go from there becomes diagnostic or insight around what happened in the hindsight. So someone can look at the information that has been plotted and say, well, this is my causation and correlation. These are why the things happened the way they did. So that's essentially why did it happen. These are all taking data points of things that have already happened in time, things that have already taken place, right? And these have very, very real usages, even in a digital twin, right? But these are just some lower level. You have to wait until something actually happens before you start doing descriptive and diagnostic analytics. When you start looking at predictive or foresight, well, what if? Okay, this is when we start thinking about, you know, what might happen. So what happens if I increase my sales by 50%? What happens if I decrease my sales by 50%? What happens if I introduce a new product line? What happens if I introduce a new building? And what's that going to do to my throughput and manpower? So all these what ifs, you start to become predictive about your analytics. And lastly, prescriptive. What action should we take, right? I can understand that what happens to my existing experiment, my existing line, if I increase my sales, but what do we do now, right? So how can we make it better? How can we make these results that I'm seeing in the predictive analytics, how do I solve those problems? Now, this is commonly referred to as a discrete event simulation. You start looking at how things are actually flowing, the analytics around it. A lot of these things can just be broken down into a very simple, easy to describe system, right? All these different inputs and outputs that we have. Now, what becomes problematic in traditional tools, things that might be spreadsheet driven or data point driven, is the computational overhead is quite large, right? So when you have simulation software that exists in the market today, it can actually drastically reduce that computational overhead by using AI-backed systems, as well as taking your variances and applying them to what's happening in the actual real-world scenario. Now, discrete event simulation is not new to the world. However, it has become extremely attainable from a cost perspective. Software like this used to sell for $20,000, $30,000. It can get down in the range of $3,000 or so for a really good discrete event simulation software. It basically is going to take the assets of your digital twin, and it can do them with 2D assets that you have from layouts that we saw in our last session, or it can also take the 3D assets and do discrete event simulation in 3D as well. So it's important to understand that the things that go into this, right? The reason why we had conversations about reality capture and building in factory assets is because all these will help with the visual understanding and acuity around an event simulation. So ultimately, we want to do this to right-size buffers, systems, and different resources that we have in a given line, right? We've all seen this on the left-hand side. Maybe I'm dating myself a little bit, right? But what happens when chocolate just keeps coming down the line and we can't keep up with it, right? So you can analyze that through descriptive and diagnostic analytics, but how do we plan to increase that conveyor line? What's going to happen, right? So let's speed it up, right? We don't want to have to wait until Lucille Ball goes through and has to eat all this chocolate and then we have all this waste. We'd like to plan for that ahead of time. So maybe we need to add another conveyor, we add more personnel, we slow it down, we create more buffers. These are all things that layout simulation will assist in. Essentially, you always want to start off with a point in time that's measurable and accurate. So you want to start off with your experiment of as-is scenarios and then start pulling levers and toggling switches that will start making changes. Okay, so for instance, very simple example here of a scenario manager where I have my baseline. The baseline experiment is diagnostic and it's descriptive. It's exactly what has happened in the past. But what happens when I add another robot, right? My conveyor speed is going to be the same. But I have a new operator and I have a cost to that operator. So I wanted to adjust and see what happens when I add this new variable in, right? So you can get a visualization of the process, you analyze the result that it gives you, and you go back and you keep optimizing the scenarios based on your outcomes. So do I need to still get the same amount of product out in the same amount of time? Do I need to get 50% more product out in the same amount of time to keep up with market demand? These are all experiments you can run. There's very little you can't simulate if you isolate the experiment the right way. So we're going to take a look at just a few examples of where this has some real life benefit, right? So it's easy to talk about simulation and experiments, but let's see where we've actually had some success with this, right? So let's look at logistics first, okay? So the problem we have here is we have a new production line. Okay, the new production line, as it's creating product, is creating congestion by the number of pallets that are en route to the warehouse, okay? You can see that building up here in the simulation. Now, the congestion we have found is caused by inbound and outbound pallet crossover. So we identified this through descriptive and diagnostic analytics. Now, our proposed solution will be to adjust the inbound and outbound pallet flow on this line so there's less congestion happening in the transportation methods. So how do we actually run this then? Well, we use our digital assets, right? They can be 2D, they can be 3D, they can be correlated. I'm just use 2D here as an example, but essentially you can see on the left-hand side our as-is situation, right? All the pallets are blocking up. We can easily determine this information. It's real life. This is what happened. Now, when we switch it around, simply by adjusting the transportation routes, we can see how things adjust differently and how we have alleviated that congestion and pallets are out to the warehouse much more efficiently. Another scenario would be around modernization. So on the left-hand side, we have a current environment, current flow, current layout of a facility. We have some analog bar feeding machines. And basically this was a plant that was built in the 1940s. Gas was cheap. We only had 6 product variances. However, it created a long changeover time based on the equipment. But hey, machines are paid for. Don't fix it if it's not broken, okay? So why should we change? Why should we invest capital? Why should we modernize? Why should we do any of these things if everything's working just fine, right? If I'm cold, I would just go in the corner and rub 2 sticks together and build a fire. Builds a fire, right? Well, let's look at what a modernization would do. Okay, so let's look at an induction heat treated system with CNC machines and a bar feeder, right? So here we're going to have a little bit more modern, agile manufacturing process. It's going to support a lot more variances and have really short changeover time. It's going to help me reduce overall inventory because I don't have that long changeover. It's going to help me reduce energy costs, manpower, and floor space, okay? But how do I prove that to somebody? Show me the numbers, right? Show me your math. Make sure the math maths, right? So how do we do that? Well, we can do that through discrete event simulation. We take our current environment, we take our new environment in a predictive and prescriptive environment and say, this is what we're going to get as a result. Okay, so we found that after analyzing it, we use 65% less energy. Here's my numbers, right? We have a little bit better throughput, not drastic, but slightly better throughput, okay? But we have a 73% reduction in energy cost. So that means I can increase my margins or keep up with other market stressors, such as maybe a competitor. So I have a little bit more wiggle room. And we also produce 69% less CO2 by not using a gas system, okay? So what does that all mean to me? Well, maybe I can get government grants for going green, right? Or having a more neutral carbon footprint, okay? It's a good investment, large process improvement that has positive environmental impact, okay? So showing this to somebody visually, having the numbers to back it up, be able to properly examine a case for why we should do something can ultimately lead you to higher margins and more product availability. So in general, benefits to layout simulations, they basically help you gain a really true understanding of a very dynamic system, as things are changing and moving out throughout your facilities. It does really give you truly predictive analytics, which you can't get with more traditional means. Now, traditional means still have value, they still have merit, right? But this is definitely helping you more in the prescriptive and predictive analytic. It helps you discover system latency and resolve maybe resource utilization. What happens when someone calls off a shift? What happens if a forklift breaks down? What happens when I have a backlog in a certain area of the process? Maybe I need to invest in a new piece of equipment to make that area a little bit faster. Maybe I need a Bluetooth torque system or something like that. Right? Help you maximize that productivity. Okay? But ultimately, if we kind of go to the bottom here, it's the virtual sandbox for doing anything with a digital twin. You've captured current state of things. You have proven experiments from a descriptive and diagnostic standpoint. So now you can start being more predictive and more prescriptive about how changes are going to be coming to your business in the future. So it's a tremendous aspect of digital twin that you can do without going to the enormous size of the completed digital twin. You can do this in a microcosm, right? You can do this in a small experiment. Okay. So what we're going to do now is I'm going to turn this over to Alan, and he's going to talk to you about a little bit different type of simulation that maybe isn't as pertinent to, let's say, flow of content and material like I showed here, but more to a simulation of different proportions. Alan?
Thank you, Mark. All right. So a couple things we want to talk about, and essentially the impact that they can play, and kind of coupled with, we're working in partnership with our factory teams and our engineering teams that have performed kind of the interior coordination and layouts and simulation. And you know, whenever you've optimized your design of your factory and the lines and the equipment, well, oftentimes those who you're partnering with in the construction end, the trades, architects, engineers, and so on, they have to build everything around you, correct? So that's where the concept of coordination, whether it be design or trade coordination, let alone simulation. And so much of the same that we were doing earlier in the earlier phases, or kind of in conjunction with the designers of your factory lines and so on, we're doing those same concepts, and perhaps just with a little bit of different lingo and so on in the phases of construction, let alone design and construction. Next. So we'll focus on coordination here, and then we will jump to the 4D simulation just to kind of get an idea of how all these things come together to really paint the most visual picture. So traditionally, we have had to do coordination one way or another, right? It's not as though we can go in and just start building and putting things together and expect that there's going to be success at the end of the day. So if you've seen documents such as the one here on the left, this is essentially a coordination of all of the trades in a 2D world. Now this is even a CAD world, but this is 2D, and it's very, very messy, and it's hard to figure out, essentially kind of like a shop drawing that helps us to understand where everything is going to go. It's color coded and so on, but as you can imagine, that's messy. And so what do we expect? What do we expect out of documentation like this? Well, it's kind of funny. We got questions. We've got what's going on here. Well, what do those equal? Well, when we're talking about the construction phase, we have what we call RFIs. These are our requests for information. So what can a request for information equate to for us as the owner of the facility, the manufacturer ourselves? Those create a time constraint. So whenever I have to ask a question, what does that question entail? Maybe an email, maybe a phone call, maybe 2 or 3 emails or phone calls, and ultimately we get something submitted to the person who's going to give me an answer on how to proceed. That could take, ultimately in construction, traditionally you have 2 weeks to respond. So if an engineer gets back to a contractor 2 weeks later, what were we doing for those 2 weeks? That has cost impact, that has real ramifications on execution of your building. And what are we always trying to get done in construction? We have to meet project schedules, and we have to meet project costs. So whenever questions arise, both of those are impacted. Next. So let's take a little bit of a deeper dive into the timelines of coordination, and when can we do that? When should we be executing these coordination tasks in the life cycle? Well, you can think of coordination also kind of the same thing as constructability review. We just need to make sure that this building is constructible. And as we'll see in a moment, you can there's a really nice graphic that helps us to understand this. But if you think about it just logically, in this first image here, we see potentially these are risers that come up to, say, some rooftop equipment. Well, eventually down the road, you're going to have to you know, you're going to have to place some sleeves in there, but ultimately that's a legitimate penetration of an interface from pipes to concrete, for instance. And that's totally legitimate. We're good to go there. We understand it. We've identified it. We can move along. We don't have to create an issue. No worries. But ultimately, if you look to the north, hey, we've got a piece of equipment, large equipment, that's going to get a construction crane to lift it into place. But we've also got, say, roof drains that are encroaching on that piece of equipment. So that's going to cause a change. I'm going to have to move that. And as you will see in a moment, we want to be able to catch these things as early as possible, so that because what is the impact to this? If I catch it earlier, it reduces the impact. And so what happens is, if I identify a location where I've got to make a change, well, that change has impacts upstream and downstream. It always does. So if I have, in this case, you've got roof drains, you've got the piping that has to go somewhere. Well, if that goes and causes a clash, you need to go detect that, and you need to figure it out so that you can move it, and we can do that as early as possible. In doing so, we're reducing those questions that happen downstream. We just identified those RFIs, right? Trade coordination is incredibly important. It's something that we in construction, it really has to happen. We know it's happening one way or another. Like we saw in the last image, it's happening in 2D and plans and paper one way or another, or it's happening in the BIM, in the modeled environment. And it's happening, as we will see later, it can happen with, obviously, building systems, but it's also going to importantly happen with the building systems that are going to serve your equipment, and how those get there. And then we'll see in a little bit more detail, some additional detail about how those affect the coordination effort and the design. But in construction, there's things that are not even considered during design, such as insulation or maybe clearance zones, things like that, you know, potentially, I should say, design teams, they're not as worried about. They're really more focused on, say, sizing and making sure that the building works and it's going to fit overall, more of a theoretical, whereas in construction, again, we need to be constructible. It has to fit. And that's why we do this in a virtual manner. All right, next. So this is a fairly good graph just to help you understand the impact of executing a task like coordination, and when it is more powerful and more effective, and why, right? So if you can see here in the X, we have the time dimension, and then we have the cost dimension, or effort dimension, I should say, in the Y. So you could see here with traditional methods, we saw that super busy document in 2D in CAD, and that's the black line there. That's a traditional method, and what we're looking at is the impact that it takes when something needs to change. If you have a traditional process where we're still having to make changes and it's moving further down the timeline, it's a more costly situation. That cost line that arches up in number 2 in the red, that's where that effort and that cost starts to grow. But if you have a modeled environment that you've simulated that layout, and you understand that, hey, I have the optimal design for the maximum production in my facility, and then my building is fully coordinated to fit around my factory lines, well, you can simulate and you can execute those changes earlier on in the design process such that it is less impactful. And again, with those, the impact of that, a better design comes out to the next phase, which is absolutely critical in some of the Ys in coordination. Next. So for some of the reasons why we might want to execute coordination, of course, the spatial coordination, We just want to make sure that, hey, these things are going to fit. And again, that's more of a design phase. Hey, is this big piece, is this big block that is a representation of what ultimately will be there, is that going to fit? And we're getting, as we continue with the design, we're continually adding the level of development and detail to our documents, ultimately get to that what we call LOD 400, level of development 400. That's the prefabrication. That's the actual virtual representation of what's going to be built, right? But again, spatial coordination, we can be very, very broad, and we can be a little bit more generic and create what we call no-fly zones. Hey, mechanical is here, electrical is here, and so on. And that's what we talk about with developing a hierarchy and understanding what takes precedence over the other, right? Your equipment ultimately is most likely going to take precedence over your building. You need to make sure that your equipment operates appropriately, and the building needs to be essentially reactive around your building. I should say around your equipment and your actual production systems. But as you can see here, there's kind of a matrix here. This is what happens during coordination. We run systems and models against each other to identify where we have the most issues, essentially a heat map. And this lets us focus our efforts and times on where there really are major problems within a building, within the systems, within the design, such that we can drill those down, reduce the issues, such that when we get out into the field and we begin to build where those huge cost impacts are incurred, that there's less issues. On top of that, what does the coordination effort get us? If it's a more streamlined building with fewer clashes and it's a coordinated facility, virtually, we're going to be able to expedite the construction phase, because what does an RFI cause? It causes time. That kicks the can down the road. We have to push out schedules that induces cost impacts, things like that. Well, again, a really organized building that has like logistics applied to it, such that we know when things have to be, when things have to occur at what phase, at what time, we're organized, that's going to expedite that process. And ultimately, this coordination effort becomes clash detection, ultimately, for instance, in the design phase, ultimately becoming clash resolution, and sign off once we're into construction and we're moving on to the next phase. All right, that's a little bit about construction. Let's take a gander at some of the 4D simulation and analysis. So, for instance, or just for example, what is 4D, right? We all understand 1D, 2D. Our 3D environment, that's really what we're focused on. But then if we want to simulate and actually bring things to life, we have to introduce this next level, which is the fourth dimension, being time. And with the advent of schedules and these Gantt charts and tying them together with our BIM, with our design, the virtual design, the 3D environment, we are able to assign a task, tie it to a BIM element, and then we're able, or a piece of equipment, what have you, and we're able to go and define when it occurs and how it occurs, and the logistics. Again, maybe it has to arrive on site, maybe there has to be a construction crane that arrives on a given day. Well, if you think about it, these are busy sites. There's many things going on at the same time, just like on the factory floor. We have to have schedule, organization, and that's where simulation becomes so important. And we'll see that here in the next slide, where when we begin to tie these things together, we take all of the information we've developed with that time, again, that schedule, and that can be the contractors. We take that with the design team and their BIM, and then they hand it off to the subcontractors, and all these systems come together. We're putting together this picture that we can turn into and bring to life. And so next slide, this is a simulation of what you're going to experience with bringing together all of these designs, the 3D, the 2D, and being able to tie them together. This right here is a timeline. We understand that we are installing equipment and it can be virtualized, visualized as you go. And then what's really awesome is when we tie that to that schedule, and you can see where we have pieces of equipment that are running into steel. And we know that in those cases, there has to be some kind of egress, there has to be safety and clearance zones. And then we tie through the timeline, or tying that to a schedule, it allows us to clash detect over time. And that cannot be more illustrative of actually being able to visualize the process, both our equipment, like Mark showed with the optimizing your actual throughput, your production. Well, that's kind of the same thing that we're doing here in the construction world. We're making sure that things are coming together at the right in the right sequence, and so on and so forth. And so at this point, we've virtualized, we have simulated, we've coordinated, we have the building fitting together appropriately. Now we've tied time to it, we've analyzed, and so at this point, we're in pretty good shape, and we should be able to move along to the next phase. And so at this point, Jason, back to you, or Mark.
Hey, I'll take this. Thanks, Alan. Appreciate it. Thank you, Mark. So in the Digital Factory series, again, this is kind of the model simulation coordination, and I think there's a lot of capability that we saw here. It's a bit of a journey for a lot of companies, but hopefully this helps you kind of get started into thinking, hey, if we could do this stuff virtually, what kind of an impact would it have on my business? And I really like what Alan showed as far as the cost curve, or the cost impact of change over time. If we can do it in the computer, it's much less expensive than having to go back and do things, fly people around, move equipment, cut out egresses in buildings, doing those kinds of things that become tremendously expensive. So as we move forward, we're going to talk a little bit more about the construction process, management, and closeout. And I'll summarize kind of what that looks like on the next slide. Mark, please. All right, so getting back to the kind of the convergence of the building and manufacturing, or design, AEC, and construction processes. I highlighted a couple of the areas that the next webinar will mainly affect, and the team will walk through that construction process, then hand off back to the owner so they can effectively operate the facility. So one of the biggest problems that we see in our customer base is the ability for owners actually to take control of documentation and construction processes. And there's a good reason for that. I think in the past, there wasn't interest from an owner of a building or factory because it was difficult. But I would argue that the cloud has changed everything. And we actually even have developed our own cloud tools. One of them called Clarity, that manufacturers use to help that process. But there's a lot of tools on the market. I'm just saying we actually participate in making that problem better as well. So I would argue that now more than ever, owners should consider taking ownership of some of the construction processes, definitely the handover process, to ensure that they obtain the proper documentation and manage it to make sure that they operate and maintain and enhance the facility as it goes along. So we look forward to that next part in the series. And I think that's it for now, Lori, and I'll turn it over to you for any questions and answers.